figure out like whoever does this, I'll do what you say. You got it.
Okay. We are going to talk about the next set of tests. Okay? These are actually going to make your life much easier. I'd rather you not. Okay.
I probably won't.
So we're going to go through two different comparison tests. The first are the direct comparison tests. Okay? So let's start with here. Okay, first of all,
The second, indirect.
what?
The second, indirect.
No.
Oh.
The second one is a limit comparison test. Okay, we're good. We're good. So here we go. I have two series where both sequences are positive. Okay? So this one converges right here. And the one that converges is bigger than this one. What must be true about A's, the series of A's again? If we have one that converges, and it's bigger than the series that we would like to figure out, then it's also going to converge. Okay? It's going to fit underneath the one that already converges. And so it should also converge. Does that make sense? We have a bigger series that is converging, so our smaller series should also converge. Okay. Vice versa, if we know that our smaller series diverges, then our bigger series will
Convert.
Okay, let's think about it. We already have a sequence that diverges. Now we have an even bigger sequence. That sum is also going to diverge. It's logical, right?
Yes.
Okay. Now, when you use this test, you have to show the inequality as a part of your work. So you have to tell me which series you're going to compare it to and how you know whether that diverges or converges. You have to show the inequality to therefore conclude the new series diverging or converging. Okay? So you're going to have to write more than you're going to have to think, if that even makes sense. Okay? What the direct comparison test is nice for are those sequences that are off by just one little thing compared to something that we already know something about. You're going to use the the direct comparison test quite a bit with like a p-series or potentially like a geometric series. Okay? A lot of times in p-series, because p-series, we can think about those quick, right? Okay. So here's our first example. Write it down. I mean, I guess if you want to.
Oh, okay, gotcha.
So we can compare this to what is a sequence or a series sequence. Okay, we know this. We're taking the sum of a sequence. What's a sequence that's very, very close to 1 over n cubed plus 1? 1 over n cubed. Okay, which we know what about?
Convergence.
We know it's a convergent p-series. Okay, compare to the sum of 1 over n cubed, which we know is a convergent p-series.
Yeah.
Okay.
Because P is greater than 1.
Now, how does 1 over n cubed plus 1 compare to 1 over n cubed?
Less than, because the denominator.
Less than.
Okay.
This is tricky.
Okay, since the denominator is bigger, it's actually a smaller sequence. And if our sequence is smaller than the sequence whose sum we know converges, then its sum also converges by direct comparison.
So you're gonna have to do the same
What?
because you could say,
You're gonna want to keep things as similar as you can, okay? Because you don't want to have to be too, like, you don't want it to be ambiguous. Is that really bigger than all the time? Okay, it needs to be something that's very clear. That is obviously always smaller than 1 over n cubed. Okay. If that was 5n cubed plus 1, it would also work to compare to 1 over n cubed. Okay.
compared to one of those.
Like I said, I would stick to as similar as you can, okay? Because we don't want to get into, you know, if you have, you said n to the 4th,
And then
you n squared.
it's technically always.
I would stick to as similar. Yes.
Sorry, kind of off topic, but is Sean gonna be like really late because
Strong has made me here today.
Because
Because,
he had schedules?
yeah, so, hi, Sean. Great, I did record.
Yeah.
Okay, thank you. And just let people write it down. Yeah, we're in here until 2:45. Thank God. Yeah, this should be a shorter lesson. Okay. So this is very, very close to what series? Okay. So we're gonna say, let's compare to the sum of from n equals 1 to infinity of 1 over 3 to the n, which is a convergent geometric series. Okay, let's look at each sequence. We have 1 over 3 to the n plus 2. How does it compare to 1 over 3 to the n? It is always less than. And since we have the sum of this sequence converging, this sequence is smaller, that sum should also converge. So since this is true, then this sum also converges by direct comparison. Do you see how you have to write more than you think?
since then,
Okay? A lot of you are going to be able to look at this problem and say, oh, yeah, that converges by direct comparison. And then you have to like write it aloud.
Yeah.
Okay? Yes.
We could write BCT.
That'd be fine.
convergence, DCT.
Direct comparison.
That's all you have.
Okay.
So even right after inequality, we're just.
I'm assuming we're also talking about indirect.
No.
Scramble.
Okay, so things that you have to have for the direct comparison test. You must say what you're comparing to and whether it's convergent or divergent. You have to have the inequality, and then you have to have your conclusion.
Oh, yeah, no.
Sorry.
Them proofs though.
Okay, so there are going to be times where our inequalities aren't going to work out the way that we want, right? Like we may try to compare something, but the inequality doesn't work out in our favor, or the inequality is a little too ambiguous. It'd be hard to show that yes, this is always true. Okay, so the direct comparison test, it's nice, it's short, it's sweet, but it's not always the best test to use. Okay, if you want to use a comparison test, but the direct comparison test isn't quite in our favor, we have the limit comparison test. Okay, now I will tell you the limit comparison tests are really nice when you have rational functions, so like polynomial over polynomial, or some sort of variation of that. Okay, and you'll see why as we do these examples. Okay, so if we have two sequences where we take the limit of their ratio as n goes to infinity, and that limit is finite and positive. No. Well,
Finite and positive. Zero positive.
0 is not positive.
So if one of them is a zero, then it doesn't work.
Well, I'm just more concerned about dividing by zero.
Okay, so they're probably not going to be 0 because we're usually starting at 1 anyway. And that's why they have them either way, because if you're going to divide by 0, you want to do it the other way. Right? Okay. So you can take whichever ratio, it's not going to matter. But the limit has to be finite and positive. So finite means
And
not infinite. Okay? Positive means
But I thought before you said not five.
not negative, not 0.
Yeah.
Okay? So if this is true, then both series converge or both series diverge. Okay? So what we're going to do is we're going to pick a series to compare it to, find the limit of their ratio, and then make a decision about converging and diverging. Okay, so this is the test that would help us with number 4, and we can go back. I mean, I don't know.
Okay, let's continue this example. Number 4.
You can't use this on number 4.
Smiley face.
You can't use this on number 4. Okay, Nick,
What if I try?
unpaired. Okay. Okay, so if we use our logic for picking a series from our last example, we would probably choose 1 over n squared. Now, do you you really wanna prove that that is either always bigger or always less than 1/n²? It's not proof, okay? So instead, we can still compare it to one over n², and we choose that because the highest power is n to the second in our denominator, right? And what do we know about the series of 1/n²? It's a convergent p-series. Okay. So then we're going to look at the limits of the ratio. You're going to see why this is going to be so nice. Okay, so really what we have instead of the ratio is one sequence times the reciprocal of the other. And if you notice, we have n² over 3n², blah, 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 doesn't matter. What's our limit? 1/3. And what's true about 1/3? Positive and finite.
We didn't
Okay,
say
I
it
said
has
it's
to
a
be-
finite number, not a finite decimal. Okay?
It might be.
Therefore, our original series will follow suit. So it will also converge by, if you want to write LCT, that's fine. I'm going to write limit comparison.
Can you use all 3 dots?
Yes, you can use the 3 dots. Okay, so like if you stick with things that are polynomial over polynomial, you're going to get like a nice limit, right? Even things that have some radicals, but as long as there's polynomials under the radicals and it's a rational function, this is going to work out really, really nice. Right?
By 1/n.
Just write it down, please. For those of us who are actually taking notes. Okay, so see, some of you can already see where this is going to go. Okay. Which is why this test is nice. Okay? Because this is a mess, right? It's a mess. Okay? But let's look at the leading term. And when I say leading, I mean like highest degree. So if this was like in a weird order, you want to look at the highest degree. We have n to the 4th over n to the 5th, which we could really simplify down to even ignore this one. 1/n. That's what we're going to compare it to. Okay? Don't worry about the coefficients. Don't worry about the rest of the garbage. Just look at the highest degree from each and simplify that. So we're going to compare to the series of 1/n. What do we know about that series? It's a divergent p-series. It's actually the harmonic series. Okay? So now the limit towards infinity of our ratio. So I'm just going to go ahead and skip to A times the reciprocal of B. that okay with everyone?
That is all.
Okay, the point of this is so that this limit works out the way it has both times. We have end to the fifth over end to the fifth. All we have to look at are the leading coefficients. What's the limit?
1, 4.
Oh, which is positive and finite.
Even in decimal
We have to
form.
make note of
Yes, we do have to make note of that.
that. 1/4 is positive and finite.
Uh-huh.
And
Therefore, our original series also diverges by the limit comparison test.
Yeah.
So then, if it didn't diverge, it would have come out to a positive and finite number.
Well, okay, so if your limit comes out to be negative or infinite, you can't use the test. It's not gonna tell you.
Okay, got it. We'll just be doing a lot of work.
That doesn't mean it converges.
Correct. It doesn't mean like the opposite. There you go. Here's your homework. Would you have time to begin? Oh, it is rough being you.
yes, it is.
Yes.
If there's like a negative sign in the original, could you like compare it to like a negative 1 over n or something?
Well, let me show you something.
Oh, dang.
Yeah.
A and B have to be
23.
positive. I'm going back.
Okay, there.
Okay, if you notice on my board, I just adjusted the days, so I didn't erase very much. So we'll do alternating series tomorrow, ratio and root test on Monday. We'll review Tuesday and Wednesday and quiz on Thursday before your 4-day weekend.
That sounds like fun. Wow.
Yeah, it'll actually work out quite nicely.
Thursday.
We will get to do a throwback Thursday.
Oh,
Yes, but I wasn't planning on having a throwback Thursday today because
We would have been doing the ratio.
You haven't done
route.
Yeah.
so this is a gift. No throwback Thursday. Okay, take it either way then.
She took away our gifts, you guys.
Aww.